Our next example is introducing a new element, not the dependent current source like we saw in the last one, but in addition to the resistor and the independent current source, we are now adding a voltage source. Okay, now look, compare this circuit to circuit 1B right here, and we see that what has changed is this 5 ohms was replaced with a voltage source. So we're going to find actually that initially what looks like a complication actually reduces the complexity of our circuit, and we actually have less to solve this time than we did previously. So let's do like before. I'm going to paste in, oops, rats. Here are the KCL equations from that example 1B. And now let's go through and get rid of or modify things as necessary. So walking through, let's go through node 1 first. This first equation will not change in any way. Now the only thing that would you might think would affect it would be that when we're looking at current that's leaving through the 20 ohms, that's this guy here, we do V1 minus V3. Now sure, that something is going to change over on the actual voltage V3, but we can still refer to the voltage at that node as V3, and so the KCL equation at node 1 is still holds, and so these do not change. Similarly, for the second KCL equation at node 2, we'll have the same thing. These are not going to change in any way if you work through that. Now it's this last equation that is going to throw us for perhaps a loop initially. So let's begin. We have the current flowing. Let's start with current flowing through the 10 ohms here. That's this second term, 0.1 mhos times V3 minus V2. That's fine. And then the current flowing up through here, through the 20 ohms, is going to be 0.05 times V3 minus V1. And then lastly, we need the current flowing down through the 10 volt source. And so this no longer holds true because we have a voltage source. So we need to write an expression that expresses the current flowing through that voltage source as a function of all the node voltages. And here is where we run into a snag, because by definition a voltage source delivers a fixed voltage independent of how much current you put through it. So there is no expression that would say V of a voltage source is equal to some quantity like an R times the current flowing through it. There is no such thing. So we might think, oh, we're stuck. What can we do? Now we step back for a moment and we remember what we're really after. We're after solving for the 3 node voltages V1, V2, V3. And if we're going to have 3 unknown voltages, then we need to have 3 equations. The question now is, do we have 3 unknown voltages? Well, it turns out, if you haven't spotted this yet, there's actually only 2 unknown voltages in this circuit now. And those 2 unknown voltages are the voltage V1 at node 1 and V2 at node 2. And the reason that I can say that is that the voltage at node 3 is connected to ground through this voltage source, this 10 volt source. In other words, this 10 volt source is stating what the voltage at node 3 will be relative to the reference node. And so this last equation is not needed, and we can't even write it, because there is no V3 to be solved for. V3, we could say our third equation, okay, equation number 3, if you will, is this, that V3 is equal to 10 volts. Now if we plug that 3 volts, that 10 volts back into the first 2 equations, we would then replace this with 10 volts And then here we would replace this with 10 volts. And we now have just two equations with two unknowns. So let's see if I can clean that up. Let's write the first KVL equation. We'll have 0.35 mhos times V1 minus 0.2 volts, 0.2 mhos times V2. And then this will be equal to 0.05 times, that's mhos, times 10 volts. Okay, now let's do this second one. Oops. Here we have minus 0.2 V1 plus 0.3 V2 is equal to plus 0.1 mhos times 10 volts. So we can put this into a matrix form again. We have 0.35 minus 0.2 minus 0.2 and 0.3, all of that times V1, V2 equal to, and here we'll go ahead and write this out. This is going to be 0.1. Now this is going to have units of amps, right? Conductivity, mhos times voltage is current. And the second term will be 1 amp. And this is our final set of equations. Only two unknowns. And we can write here, and V3 is equal to 10 volts. So the takeaway is, if you ever see a voltage source in a circuit for which you're going to use nodal analysis, and if that voltage source is connected between one of the nodes and ground, then you do not need to write a KCL equation at that node. You don't need to write one because there is no unknown voltage at that node to be solved. The voltage at that node has already been constrained by the voltage source that connects it to ground.